CPU scheduling. CPU scheduling is the vital process of determining which process gains control of the CPU for execution while other processes wait. Its primary objective is to ensure that whenever the CPU is available, the operating system selects a process from the ready queue for execution. This selection is orchestrated by the CPU scheduler, which picks a process from memory that is prepared for execution. CPU scheduling encompasses preemptive and non-preemptive approaches. Preemptive scheduling prioritizes tasks, allowing higher priority tasks to interrupt lower priority ones, which then resume later. On the other hand, non-preemptive scheduling allocates the CPU to a specific process without interruption, making it versatile across hardware platforms. CPU scheduling algorithms aim to optimize several key criteria in managing processes efficiently. These include maximizing CPU utilization to keep the CPU consistently busy, increasing throughput by maximizing the number of processes completed within a given time frame, and minimizing turnaround time, which refers to the time taken to execute individual processes. By balancing these factors, scheduling algorithms strive to enhance overall system performance and resource utilization. In CPU scheduling, several key terms play crucial roles. Throughput refers to the number of processes completed per unit of time. Burst time, or execution time, signifies the duration a process needs to execute on the CPU. Arrival time indicates when a process enters the system for execution. Waiting time is the duration a process spends waiting in the ready queue before it gets CPU time. In computer systems, every process necessitates time for execution, which comprises CPU time, the duration the CPU spends executing the process, and I/O time, the duration for input-output operations. Typically, I/O time is disregarded, focusing solely on CPU time. Burst time denotes the overall duration a process takes to execute on the CPU. In the context of process scheduling, the arrival time denotes when a process becomes ready for execution. In a specific scenario where three processes are considered, their arrival times are 0 milliseconds, 1 millisecond, and 2 milliseconds respectively. Waiting time in the context of process scheduling refers to the duration a process remains in the ready queue awaiting CPU execution. For instance, if three processes with arrival times at 0 milliseconds, and 2 milliseconds are managed using the first-come first-serve algorithm, the waiting time for each process would vary depending on their order of arrival and scheduling. The waiting times for three processes are as follows. P1 has a waiting time of 0 milliseconds since it starts immediately upon arrival. P2 waits for 8 milliseconds because it must wait for the completion of P1, and its arrival time is at 0 milliseconds. P3 waits for 13 milliseconds as it follows P1 and P2, thus starting after 8 plus 7 equals 15 milliseconds, and given its arrival time of 2 milliseconds, its waiting time is calculated as 15/2 equals 13 milliseconds. 6 primary types of CPU scheduling algorithms govern the organization of processes in computer systems. These include first-come first-serve, shortest job first scheduling, shortest remaining time, priority scheduling, round-robin scheduling, and multilevel queue scheduling. Each algorithm employs distinct criteria to determine the order in which processes are executed, contributing to efficient resource allocation and system performance. The optimization criteria for scheduling algorithms include maximizing CPU utilization, throughput, and minimizing turnaround time and waiting time. These criteria are crucial for enhancing the efficiency of CPU usage through effective scheduling techniques. The first-come first-serve scheduling algorithm prioritizes CPU allocation based on the order of process requests. It operates on a first-come, first-served basis, utilizing a FIFO queue to manage jobs. While straightforward and simple, FCFS tends to perform poorly with high wait times, making it less efficient compared to other scheduling methods. In this example of first-come first-serve scheduling, there are three processes with respective burst times, P1, 24, P2, 3, and P3, 3. The processes arrive in the order P1, P2, P3. The FCFS scheduling Gantt chart shows the waiting times for each process. P1 waits for 0 units, P2 waits for 24 units, and P3 waits for 27 units. The average waiting time is calculated as 0 plus 24 plus 27, 3 equals 17 units. In this example of first-come first-served scheduling, 3 processes with respective burst times arrive in the order P2, P3, and P1. The resulting FCFS scheduling Gantt chart shows waiting times for each process. P2 waits 0 units, P3 waits 3 units, and P1 waits 6 units. The average waiting time, calculated as the sum of individual waiting times divided by the number of processes, is 3 units. This represents an improvement over previous cases, indicating the efficiency of the FCFS algorithm in this scenario. The Convoy Effect, tied to the first-come first-served algorithm, describes a scenario where the entire operating system experiences a slowdown because of a few sluggish processes. It occurs when shorter processes are queued behind longer ones, exacerbating delays and diminishing overall system efficiency. Shortest job first scheduling is an algorithm that prioritizes processes based on their shortest execution time, ensuring that the briefest task is executed next. By minimizing waiting times for other processes, SJF effectively enhances overall system efficiency. Its emphasis on shorter jobs optimizes job output, leading to quicker turnaround times and improved performance. The example demonstrates shortest job first scheduling, where processes arrive at specific times with respective burst times. The scheduling follows a Gantt chart depicting the sequence of process execution. Calculating the average waiting time yields 7 units, derived from the sum of waiting times for each process divided by the total number of processes. Shortest remaining time scheduling allocates processes to tasks based on their proximity to completion, ensuring newer processes don't delay older ones. Typically utilized in batch environments prioritizing shorter tasks, SRT prevents longer processes from monopolizing resources, enhancing overall efficiency. In the example of shortest remaining time scheduling, we incorporate varying arrival times and preemption. Consider processes with arrival times and burst times as follows: P1, arrival time 0, burst time 8, P2, arrival time 1, burst time 4, P3, arrival time 2, burst time 9, and P4, arrival time 3, burst time 5. The SRT scheduling Gantt chart depicts the execution timeline. The average waiting time is calculated as 6.5 milliseconds. Priority scheduling is a process management approach that assigns priorities to processes, typically through integer values. The CPU is allocated to the process with the highest priority, where smaller integers signify higher priority. However, a notable issue with this method is the potential for starvation, where lower priority processes may never get a chance to execute. In this example of priority scheduling, 5 processes, P1 to P5, with their arrival times, burst times, and priorities are listed. The Gantt chart shows how these processes are scheduled, resulting in an average waiting time of 8.2 milliseconds, calculated by summing the waiting times for each process and dividing by the total number of processes. Round-robin scheduling is a foundational and straightforward algorithm used in multitasking environments. Its name derives from the principle of fairness, where each process receives an equal share of CPU time in turn. As one of the oldest scheduling methods, RR ensures that processes are executed without the risk of starvation, making it a commonly employed approach in various operating systems. Round-robin scheduling allocates a time quantum, typically ranging from 10 to 100 milliseconds, to each process in the ready queue. Once a process consumes its allocated time, it's placed at the end of the queue. With n processes in the queue and a time quantum of q, each process receives 1n of the CPU time, with each allocation not exceeding q time units. This scheduling ensures that no process waits longer than n1 q time units. In the example provided, a round-robin scheduling algorithm with a time quantum of 4 is illustrated using 3 processes, P1 with a burst time of 24, P2 with a burst time of 3, and P3 with a burst time of 3. The RR scheduling Gantt chart displays the execution timeline of these processes. RR scheduling tends to have a higher average turnaround time compared to shortest job first, SJF, scheduling but offers better response times. To optimize RR scheduling, the time quantum, Q, should be significantly larger than the context switch time, typically ranging from 10 milliseconds to 100 milliseconds, with context switch times below 10 microseconds. The time quantum in scheduling determines how long a process can run before being interrupted, impacting fairness and responsiveness. A shorter quantum improves responsiveness but increases context switch overhead, while a longer one reduces overhead but can worsen responsiveness. Context switch time is the duration to switch between processes, crucial for efficient multitasking and system performance, often minimized through hardware optimizations and efficient scheduling algorithms. Multiple-level queue scheduling is a scheduling algorithm that organizes the ready queue into multiple separate queues, each catering to processes with distinct characteristics such as priority or memory size. Processes are assigned to a specific queue based on their properties. Each queue operates with its own scheduling algorithm, and priorities are assigned to each queue accordingly. This approach allows for efficient management of processes with different requirements, optimizing resource allocation and system performance. Algorithm evaluation for CPU scheduling in an operating system involves a systematic approach to selecting the most suitable algorithm. This process begins by establishing criteria and then assessing various algorithms based on those criteria. Deterministic modeling is employed, utilizing analytic evaluation techniques to gauge algorithm performance under specific workloads. For instance, a common approach involves evaluating how algorithms handle a predetermined workload scenario, such as 5 processes arriving at time 0. Through this methodical evaluation, the most efficient algorithm for the given circumstances can be identified. The evaluation of 3 scheduling algorithms first come first served, shortest job first, and round robin reveals their respective average waiting times. FCFS exhibits an average waiting time of 28 milliseconds, while SJF stands at 13 milliseconds, and RR at 23 milliseconds. Thank you for watching.